Uh, so today we are going to continue our discussion on light emitting diodes. So we briefly mentioned about the characteristics of light emitting diodes, that they are small in size compared to the incandescent lamp sources which we discussed in the previous lecture, and they are rugged, and they actually provide in a small space a significant amount of brightness as well. Okay, so okay, fine. So in the case of white LEDs, which have been developed over years, and their performance has been improved, they have actually already surpassed the incandescent lamp applications, incandescent lamp use in many different applications that we are going to discuss in the application section. And then what are the wavelengths or the light wavelengths which we can obtain from the LED. So the LEDs which have been developed over years based on different materials, the LED spectrum basically varies from near UV to near IR. Okay, so one has the entire visible spectrum available with us. That means different LEDs are available at different colors. At the same time, we have near UV as well as near IR, and they have peculiar applications. Apart from the visible range, what are the applications? So I've just mentioned here, but anyhow, we are going to discuss the application in detail. But as you can see, the spread of the applications is wide, right from automotive to aviation industry, like large area displays. Then we use them in communication systems with optical fibers. Then in medicine and agriculture also the use has been explored. Then amusement media, because many of them use different light sources. There these are of use. So what we'll now go through some basics of LED. So LED is basically made up of semiconductor devices. So the material which is used is basically semiconductor, but not silicon or germanium, which is used to develop other electronic devices. So we use special semiconductor devices for building LEDs, and the LED is basically works on the principle of electroluminescence that we also discussed to a certain extent, where it involves carrier injection into the PN junction, and basically, since it is a diode, we operate it in a forward region, and the forward bias basically drives the current through this PN junction, and then the excess electron hole pairs enter into the depletion region at the junction interface that we already know, similar to the normal diode working principle. But here, in the case of silicon and germanium diode, we know that once these electron hole pairs enter into the depletion region, and there is a recombination process which goes on, when the electron comes back to the lower energy state from higher energy state, the dissipated energy, typically in the case of silicon and germanium, is in heat, right? With silicon diodes, the dissipation occurs in heat. However, in the case of specific semiconductor device materials, which we are going to discuss, such as gallium and arsenide, gallium arsenide and all. So those materials, the energy dissipation occurs in the form of light. Okay, so the recombination of the electron and hole pairs occurs in two types. One is spontaneous radiative process, and other is non-radiative process. And that is why because the energy dissipation is occurring in the form of a radiation, not only visible but as we just discussed, UV and IR, this type of electroluminescence is called as injection electroluminescence, because the uh, energy which is supplied for obtaining the luminous effect is through carrier injection into the PN junction, right? Now here the energy emitted of the energy of the emitted photon and the wavelength of the LED light depends on the band gap energy of semiconductor materials of which the LED is made up of. Okay, and since it is a function of the semiconductor material. Different semiconductor material will give us different wavelengths, right? So that's why for a green LED, let's say, the material is different. For red LED, the material is different, like that, because the wavelength is a function of semiconductor material, and specifically the band gap energy of semiconductor material. So to represent it in the form of an equation here, h nu is the photon energy, and which is equal to the band gap energy of semiconductor material. And what is the band gap energy? It is nothing but the energy difference between conduction band and valence band of the semiconductor which is used. And as we know, h is the Planck's constant, mu is the frequency of the emitted light. Now, if we according to this Boltzmann distribution, what it says is that the average kinetic energy of electron and holes when they move through the p-n junction, when in the influence of the external magnetic field, the average kinetic energy is equal to the thermal energy. What is K? This is the Boltzmann's constant, and T is the temperature in Kelvin. Okay, and when this quantity, this thermal energy, happens to be very much less compared to the band gap energy, then one can actually approximate the emitted photon energy with Eg. So that the one which we just wrote here, it is under the assumption that under the fact that the thermal energy is usually in the case when it is less than the band gap energy, we obtain this relationship, and based on that one can relate the band gap energy with the wavelength, right? So if you know the band gap energy associated, because these two are constant, so if you know the band gap energy of a semiconductor material, and if it is suitable, of course, for the purpose of building an LED, then one can associate the corresponding wavelength with that, right? So I think we also saw the one example we also discussed, I think, if I remember correctly. So at the room temperature for gallium arsenide, the value of band gap energy is 1.42 electron volt, and if you substitute it here, then the corresponding wavelength comes out to be 870 nanometer. Okay, this is near IR region, gallium arsenide. Okay, now now this is about the wavelength. Now what about the emission intensity? What about the emission intensity? So how, on what parameters the intensity of the emitted light depends? So here, as you can see, that it is proportional to the energy of the photon, right, and the temperature and the band gap energy as well. So it is a function of this quantity, and it is proportional to the square root of E minus Eg. This is the expression. Now, based on this equation, it has been derived that the maximum intensity, we are not going to look through the derivation of this. It is available in other references, but for our purpose, one can simply use this fact that it has been derived that the maximum intensity of the emission spectrum, because although we are saying that the wavelength which is emitted by the light by the LED is of this wavelength, but we'll see that it actually emits a spectrum around that lambda. Okay, so in that case, the maximum intensity of the emission spectrum is obtained when E is equal to, that is the photon energy is equal to Eg plus half of KT, where KT we also saw that it is nothing but the thermal energy. Okay, so and when you actually plot the maximum intensity, let's say this is 1 normalized, if I normalize it to 1, the maximum intensity occurring at certain wavelength lambda, okay, then the width, the full width half maximum corresponds to the difference or the difference between the photon energy of 1.8 kT. Okay, now what I'm talking about this is the intensity, which is of course function of the photon energy, and this is lambda. So if you find out the half of the intensity, that width corresponds to the width of the photon energy equal to 1.8 kT, and then that corresponding, because we now need to see what is the corresponding delta lambda, right? And that delta lambda is equal to that corresponding to the full width half maximum in terms of wavelength. The delta lambda is lambda into delta E by Eg. Okay, so this is the these are the expression which are associated with a typical LED. So for gallium arsenide also, one actually can it is reported that for gallium arsenide, when the emission spectrum maximum is at 870 nanometers, the example which we just discussed, the corresponding delta lambda is 28 nanometer. Okay, 28 nanometer. Now here one can see that even though this is significantly large, actually if you look at the lasers, the delta lambda, which we call it as the line width, is on the scale of like this or something. Okay, very small, but this is quite large. But still, we are able to see the LED as a monochromatic source. Means a red LED will look, red color LED will look like red only, as if it is emitting only red color of a particular wavelength lambda, or but we must understand that there is associated line width which is significant in the case of LEDs, but in the case of laser, which you see later on, it is very less. Fine. So although LEDs are associated with different colors, we can call them as quasi monochromatic or something. They are not perfectly monochromatic light sources. Now in this case, this delta lambda not only is associated with delta E, that is the difference in photon energy, it is also it also depends on the dopant concentration level of the PN junction. So based on the concentration also, the output spectrum changes. Now for typical LEDs, the different type of LEDs, the delta E actually takes the value between 2.5 to 3 kT. This is the typical value of photon energy. The difference in photon energy, or we can say the variation in photon energy associated with the output spectrum. Now, it is interesting to see that even though, let's say if you plot, in the previous case, I plotted this thing. So let's say this is the peak wavelength. This is the peak, and the corresponding wavelength is this in the output spectrum. But this peak wavelength is mentioned in the data sheet of given LED, but it is of little practical significance, because if let's say in market you buy 2 LEDs, and in the data sheet is also mentioned that the peak wavelengths are same, but the color perception might be different in both the LEDs. Sometimes it happens, and that is why many times the dominant wavelength is also provided along with peak wavelength, which is more important because it is the wavelength which correspond to the color perception, what we are seeing with our eyes. The color which is visible, the LED color, that wavelength is called as dominant wavelength, and it need not be same as the peak wavelength. Okay, because remember the vision, the color is what we are observing is due to the combined effect of this output spectrum, right? So it may need not be the same as peak wavelength. That need to be kept in mind. Now the output intensity is determined by the current through the PN junction. So the because in the case of LED, when we forward bias the LED, then the intensity with which the output light is obtained, it is basically determined by the current which is flowing. And let's say if I put a resistor, then I can control the current through that, right? So it basically is controllable and determined by the current through the PN junction, and the current uh, uh, the increase in the current increases the injection of minority carrier concentration, and essentially that will lead to the recombination process and the subsequent operation in the electroluminescence principle, and accordingly we get the we get more intensity. And it has been observed that at low currents the intensity increases linearly. Okay, so if you typically look at the plot of an LED, so it looks linear. So for the current, let's say an intensity, let me write as current as input and intensity as output, so it is linear. But at higher intensity, or sorry, at higher current, it actually saturates, or it becomes non-linear, not exactly saturated, but it becomes non-linear. It doesn't follow the linear characteristic. So that must be understood. So this is the important fact, that at low current only the intensity is linearly related to the input current. Otherwise, it is non-linear. And at the same time, uh, the at high current, the spectrum also means the this spectrum. Okay, this spectrum also might change. Okay, the spectrum might also change at higher currents. Fine. Now, this is one more important quantity associated with the diode, turn on voltage. Now, it is a very common question which is asked to students in their BTech second year or third year, that when they build the LED based circuit, electronic circuit, mostly many electrical, many practicals, you will be using LED as a output device. If you use this, then the first question asked is that how are you going to select the resistor? How do you select this resistor, series resistor? So typically the specification which is given is that you have to maintain 20 milliampere current through the diode. Okay, so typically it is specified that you need to maintain 20 milliampere current through the diode. So how are you going to choose the resistor? Of course, it depends on the source voltage. Let's say this is 5 volts. Now the simple calculation is, if I want 20 milliampere, I need to find out the voltage drop across. I need to know the voltage drop across diode, and if I subtract it from 5 volts, I can easily find out the value of resistor. However, many of the student, they take the value as 0.7 volts. But remember, this is not silicon diode. Okay, so the turn on voltage means we know that, or you can also say that knee voltage, beyond which the diode starts conducting, right? So even if it is forward bias, until the voltage crosses 0.7 volts, then it won't conduct. So after that it conducts immediately. So this voltage is nothing but the turn on voltage. And for silicon diodes, although it is 0.7, for semiconductor diodes, it depends on the band gap energy of the semiconductor. And as I mentioned, different colors, to obtain different colors, you need different materials. And since different material have different band gap energy, the corresponding turn on voltage is different. Okay, corresponding turn on voltage. So as you can see, blue LED, it is quite large, 3.5 to 4.5 volts. For yellow LED it is 2 volt. For IR it is 1 volt. And typically the red and green LEDs which we use, although you have to take very specific voltage, but typically we take it as 1.5 or 2 volts. Okay, not 0.7 volt. This you should remember if you are using LED in your electronic circuit. The turn on voltage should be considered based on the given specification, in designing the component values. Now, as I mentioned, LED is usually operated at constant current regime. Okay, because the once the LED turns on, then it comes to an equilibrium, and at that the current has to be maintained constant, and that's why, as I mentioned, in the design, usually it is specified that to obtain appropriate brightness, you need to maintain, let's say, 20-30 milliamperes through the LED. This is specification. Nobody will tell you that how much voltage you should apply across the diode. It is usually the current which is specified. So I hope you have understood this point. Now, let us now consider the effect of ambient temperature on the performance of LED. Okay. Here, the important fact is that the increase in temperature actually has the effect on the intensity of the LED, output intensity of the LED, and it is mentioned, as you can see here, that increase in temperature actually causes decrease in the intensity. And why does it occur? Because as we know that in the process of the combination, the PN junction also heats up, and the emission intensity depends. That is why the emission intensity depends on the ambient temperature. And if that, in order to maintain that equilibrium, if the output temperature is higher, then the dissipation will have an effect on the decrease in intensity of the output light, and at the same time the required forward voltage drop also decreases. Okay, means this the sorry. So in this circuit, let's say, so in an equilibrium condition, let's say some current is flowing, constant current is flowing, and it is emitting at certain intensity. So if the ambient temperature changes or increases in this particular case, then what will happen is even the forward voltage, the voltage drop across diode will decrease, and it will essentially increase the current, isn't it? And it will again increase, it will try to bring the intensity back to the original value, because the entire system will try to come back to the equilibrium, but it will also increase the temperature. So to a certain extent, it is observed that with increasing ambient temperature, there is a decrease in output intensity. And at the same time, not only the intensity, the entire spectral power distribution shifts in the direction of longer wavelengths. So let's say this is the typical spectrum associated with your, so let's say this is intensity, this is lambda. Okay, this is a spectrum, output spectrum, and with increasing temperature, so let's say this is for T1, then if I increase it to T2, then you will see that it will actually shift to longer wavelengths. So even the spectral characteristic also changes with temperature. So the current and temperature stabilization is essential if in certain application you need to maintain the spectrum constant. If you want to maintain the spectrum constant, then the current and temperature must be stabilized, and that's why in certain applications the LEDs are provided with heat sinks. LEDs are provided with heat sinks in order to take away the heat produced during the operation, and in order to maintain the temperature such that the spectral power distribution doesn't change. Okay, so although you might have used LED many times, but remember that the application which you are using for was very limited. But as we'll see later on, it has huge applications, and depending on that, these peculiarities must be considered. Okay, that, as I mentioned, the heat sink and all these things are provided. Now, there are few factors associated with LED which are important to take into consideration. The first one is the internal quantum efficiency. So how is it defined? So it is basically a ratio of number of generated photons in the active region, that is the depletion region of the PN junction diode, and to the number of injected electrons. So in this, so let's say this is your active region. So you are inserting electrons, right? Injecting electrons, and what you are expecting from that, like when you are applying electric field, supplying electrical energy, you want something in the form of optical energy, right? So the ratio of number of generated photons in the active region to the number of injected electrons, and ideally this quantity, internal quantum efficiency, should be 1, because each electron after recombination should emit 1 photon. Okay, but it doesn't happen. Practically it doesn't happen due to various aspects, that there is the concentration is not enough, or even the material which is used, this p type and n type, are not of good quality. So all these things, and there are also defects in the material itself, apart from its quality. So these are going to affect your efficiency. So high material quality, low defect density, and low trap concentration are essential criteria for high internal quantum efficiency. So what you really want is the amount of electric field or electric energy you are providing. You want the output energy in optical form being converted with high efficiency, as high efficiency as possible. So this is one. This is internal quantum efficiency, okay, associated with the generated photons in the active region. Now we have another quantity called as extraction efficiency. Okay, fine. The number of photons are generated, but not all the photons, okay, are available at the output. So the quantity which defines the number of photons that leave LED per number of photons that are generated in the active region. That means not all the photons that are generated are able to leave the LED structure. Okay, some get actually trapped. So it basically defines the probability of the photon to escape from LED. Escape probability of the photon, and it is sorry to mention the efficiency here. So one cannot measure the number of photons, right? Like it is difficult. So what is the measurable quantity in the case of number of photons, and in the case of number of electrons? One can measure current. So current divided by the charge of electron, and what one can measure is the output power, optical power or energy, divided by the photon energy. This quantity will give me the number of photons. This quantity will give me the number of injected electrons. And this is how this quantity is quantified. On the other hand, the extraction efficiency, since it is the ratio of photon emitted, so this is the one which is available in the space, okay, and this is the internally generated photon. But then where does this remaining photon go? So this loss in light occurs due to the reabsorption of the emitted light within the LED structure itself. Okay, within the LED structure itself, and it is also due to the total internal reflection. Because remember, we'll see that the semiconductor are also associated with the with particular refractive index, RI, refractive index. So there is interface semiconductor to air, right? And different semiconductor materials which are made up, which are making this complete LED is made up of, they also have different refractive indices. So the emitted photon gets trapped into this due to the effect of total internal reflection as well. And in fact, it is very difficult basically to to improve this extraction efficiency. Okay, it's quite difficult. Hmm. So as I mentioned in the previous case, the internal efficiency can be increased by using high quality material and making sure that there is low defect density, but achieving this is not easy. Okay, and the refractive index as most of the semiconductor is quite high, like greater than 2.5, and as a result the critical angle for total internal reflection, this is PIR, hmm, total internal reflection at the interface of semiconductor area is less than 20%. Okay, so as a result what happens is that very small cone uh, uh, area, a cone is available for the light to escape, and as a result only few percent of light which is generated in the semiconductor is able to escape the planar LED, the structure, the most commonly used structure, that is planar LED. And to better quantify the external efficiency, because we can't quantify the internal number of photons generated, we only have the availability of this one. So the it is expressed with this, where it is 1 by 4 the refractive index of air divided by refractive index of the semiconductor, the ratio of that square. This is how the external efficiency, extraction efficiency is defined. Extraction, okay, not external. External will come later on. Okay, so in this, the materials such as gallium arsenide, gallium nitride, and light emitting polymers have low refractive index. So they are designed in such a manner that they offer low refractive index, and essentially what happens is, since this is in denominator, you can see lower value of NS will actually improve the extraction efficiency. At the same time, the light efficiency is also enhanced by dome-shaped epoxy encapsulants with low refractive index. So you might have seen that if you look the LEDs closely, let's say these are representing the electrodes. This is positive, negative. So you might have seen that it comes in a dome shaped, right? LED comes in a dome shaped. It is basically to increase this extraction efficiency only. Okay, because what happens is, this material which is used, that material and air, okay, the refractive index is such that there is less internal like the total internal reflection is less, so most of the light is allowed to pass or transmit through the LED. It is not getting reflected inside. Okay, so that is why this dome shape is provided. At the same time, this dome shape also allows to generate the spherical beam of light. Okay. So in fact, the extraction efficiency optimization is based on modification and improvement in device geometry, this entire geometry, and it is an important domain of research as well, that a lot of research also goes on into this. Because what happens is that even though it is significant improvement has been done in the design of this geometry, the efficiency is still 10 to 20% only. Okay, so if you don't use this, then it is even less than 5%. The efficiency means most of the light doesn't even come out of LED, which is being generated. Now comes the other quantity, which is external quantum efficiency. This is extraction efficiency, this is external quantum efficiency, which basically now relates the number of photon which is emitted now from the LED, the one which are available to us in free space, and the number of injected electron hole pair. So it actually combines the two efficiencies, that is, this is the number of photons emitted, and this is nothing but the number of electrons injected into the material, and you can see that it basically nothing but the product of the internal quantum efficiency with extraction efficiency. And in fact, if you see that if you use the indirect band gap semiconductor as a material to design LED, then the efficiency, external efficiency, is less than 1%, and it is less than 20%. Up to maximum it can go up to 20% if you use direct band gap semiconductors. So this is an important fact. And in fact, with this efficiency, you will see that the LEDs are highly efficient in comparison to your incandescent lamps. And that's why in many applications they have been replaced. The incandescent lamp have been replaced by LEDs. Another term which is related to the LED is the radiant efficiency, that is the output energy with the input power, because this was related to the number of electron hole pairs. Here this is related to the input power. This is so this we also saw in the definition of radiative quantities, right? Now the light intensity in air, if you take a LED, let's say, and if you try to measure the intensity IR, so this is, let's say the distance is R. So the light intensity in air at a distance R from the planar LED is given by this expression, where this is the output power of LED and this is the value of R, that is the distance between the LED and the point where we are measuring the intensity, and NS is again the refractive index associated with the semiconductor material, and theta is the observation angle. Okay, observation angle. That means so let's say this is the perpendicular. So this angle is the observation angle. So as you can see that as this theta increases in this direction, you will see that this quantity decreases and it becomes of course 0 in this direction, right? In this direction. So this indicates that the LED does not have same intensity in all directions because it is directional. In fact, the planar LED has, let me draw the okay. Is the screen visible?
No, sir.
It was visible up to this point, no?
Yes, sir.
Now is it visible?
Yes, sir.
Okay, fine, thank you. So as you can see that if you use a planar LED, then if I plot, so the theta varies from, let's say, this 90 degree to 90 degree plus minus, let's say, and this is, if I keep my LED source here, this corresponds to theta equal to 0. Then if you plot the intensity of a planar LED, then the distribution comes like this. Okay, the pattern, the intensity pattern which is observed, or the decrease in intensity, if I treat this as 1 and this as 0, as you can see at 90 it is 0 and it becomes half. It becomes half at approximately 60 degrees. Approximately 60 degrees. So this is for the common planar LEDs. But then differently shaped LEDs have been manufactured or fabricated in order to improve the radiation pattern. Okay, so the radiation pattern, that if you observe that it is equal everywhere, intensity is same everywhere, this is observed with, so let me write, this is planar LED and this is hemispherical LED. Okay, now where is this hemispherical LED will be useful? Can someone tell the application or think of an application? Till that time I will draw another one. In which application this hemispherical can be used? If means a LED with this characteristic, that it is, its intensity is equal in all directions from the normal.
Sir, in LED display, sir.
LED display.
Yes,
Right.
sir.
So if I look at the screen from different angle, I should be able to see the same scene, isn't it? Right. And similarly, in the case of remote also, when you use remote in your house, you would not like a remote which will only work when you are pointing it perpendicular to the TV surface, isn't it? You want to operate it from different angles from in the living room. So in order to use that, in order to obtain that, one has to use an LED, because there also in the remote you have IR LED. So it has to be of this type, so that anywhere you point to the source, let's say this is a detector. If I'm pointing the LED in this direction, let's my remote here, then the light emitted from here should be detected and the command should be taken. Otherwise, what will happen is I have to always point the remote in this direction perpendicular, which is not always good, right? It is discomfort for the user. So in that case, these hemispherically shaped LEDs are used. But in certain application, you do need an LED which should emit in particular direction or in perpendicular direction. So in that case, you have these parabolically shaped LEDs where it is confined, the intensity is confined in certain direction. So depending on application, the different shapes are fabricated. Okay. Now, as I mentioned previously, the wavelength of the LED output depends on the material. So you have huge list of different materials which are used, but as I mentioned, the silicon is not used as it is, of course, because the emission is mainly in the form of heat, not in the optical regime. So different materials are used. The popular ones are gallium arsenide and all, and the combination of these. So this table gives an overview of different colors and the corresponding wavelength ranges which are obtained uh, from the combination of different materials. So here the ultraviolet LED, which is emitting in the range of wavelength less than 400 nanometers, it can be manufactured with this aluminum nitride, aluminum gallium nitride, like that. So you can see that the forward voltage is also mentioned here for the typical LED. So the driving voltage for this will be larger than the driving voltage for this, right? Because the drop of LED is like significant, 3.1 to 4.4, and different materials are also mentioned here. So even you can see that even though we are saying that green, so green is for our eyes, green means the wavelength range ranging from 500 to 570. Of course, the shades will be different for each wavelength depending on the person. It is subjective also, that how one sees a particular color, but typically the range is 500 to 570 nanometers. So the one we have a laser in our lab, uh, which is a red color laser whose wavelength is 633 nanometer. Okay, so you can see the red is between 610 to 760, and different materials are used. This can so you can see that it is also the abbreviation is also given. And here the important class of commercially available semiconductor materials covering the visible spectrum means this one, this one. So you can see here that this gallium arsenide phosphide, you can see it is generating orange, it is also generating yellow. Gallium phosphide is green, and yes, you can see gallium arsenide phosphide, which is generating red also. So a different combination of this material allows us to obtain the wavelength in the visible spectrum. That's why it is most commonly used semiconductor material. So here Y is the quantity which defines the percentage of arsenide and phosphide which is used in making the LED. So if this Y happens to be less than 0.45, then the semiconductor is direct band gap semiconductor and it is highly efficient. However, on the other hand, if if it is less than 0.45, you can see that the concentration of the amount of arsenide is more. On the other hand, if it is greater than 0.45, it is less and the corresponding phosphide is more. So the gallium phosphide actually introduces the indirect band gap part in the semiconductor, and of course based on Y, the corresponding wavelength will also change. So for example, here you can see if Y is 0.45 means gallium arsenide with the contribution of this much and phosphide with contribution of this much, then the corresponding LED will emit red light with wavelength of 630 nanometers. On the other hand, if I have no material, no arsenide used, sorry, no phosphide used, sorry, that means Y contribution of phosphide is 0, then it is only gallium arsenide, then it goes to it emits the light in IR range, near IR with 870 nanometers. Okay, so you can see that the range with which it can emit is significant. Like it is widely used for green, yellow, and orange. Even it is mentioned in the previous table. You can cross check that. So widely used in obtaining these many colors. And at the same time, the limitation of this is that it is providing low brightness. So the brightness associated with this material, LED made up of this material, is low. It cannot be used for high brightness applications. On the other hand, the high brightness LEDs which are used in green color, let's say I want a green color LED but with high brightness, then I cannot go with gallium arsenide phosphide combination, but I have to go with gallium indium nitride. Okay. On the other hand, if I want red color only, then I have to use aluminum gallium arsenide. So again, this is these combination of materials have been identified with different experiments and all, and they are now become standards. Of course, new materials are being introduced time and again, but as of now, These are the material used for obtaining high brightness LED. And in order to obtain the range again, then you have the combination. You can see aluminum, gallium, indium phosphide, which can give the color in red, orange, and yellow region. Now, in the development of LEDs, these different color LEDs were obtained one after the other, but obtaining blue was not that easy. Okay, in fact, if I'm correct, the one who invented blue LED got Nobel Prize. If I'm correct, I don't know. I have to cross verify, but you can check yourself that the one who actually invented blue LED got Nobel Prize. It was a technically difficult task, but in the end, it was achieved. And the gallium indium nitride was the material which was used for obtaining high brightness blue LED. Now we have all the colors available in the visible spectrum. So then with different colors, how can we achieve white LEDs? And as we know that white consists of all the colors means all wavelengths. But we also mentioned that the particular semiconductor material will have a particular wavelength range, isn't it? But then in order to obtain the entire spectrum, means in the output spectrum, in order to obtain the contribution from entire spectrum, in order to visualize the white light, it is not the particular material is not available, right? Because it is specific to particular wavelength. So in this case, the principle of phosphorescence is used in the case of white LEDs. So here, what actually happens is that a short wavelength light is emitted from an LED itself, which pumps a wavelength converter, which re-emits the light at longer wavelength. That means white LED basically consists of a colored LED only of short wavelength, which actually pumps the wavelength converter to re-emit the light at longer wavelength. And the combination of the short wavelength and long wavelength basically gives us the white colored LED. So the output spectrum, that's why, as I said, there is a short wavelength, there is a long wavelength. That's why the output spectrum of LED consists of at least two different wavelengths. So if you look at ideally what you should look like, so if I want to plot the spectrum, ideally white light should look like this, isn't it? In the visible range, of course. But it looks like this. There are two distinct different wavelengths, short wavelength and long wavelength, of which the output spectrum is consist of. But of course, the overall effect, you will see it as white. Even in the white light, you can even see some faintness of a particular color also due to this effect, because it is not uniform. The spectrum is not uniform. And the two important aspects, quantities which are essential in defining the quality of a white LED is its luminous efficiency and CRI, color rendering index. Because white LED is mainly used for illuminating purpose, illumination. Your lamp. Now previously you might have, we discussed that incandescent lamps were replaced by fluorescent tubes, right? And now they have been replaced by LEDs because of their high efficiency, right? So since they are used for illumination purpose, when you are illuminating an object, what is the basic criteria? That it should actually give us the same perception of the actual color of the object. So that is quantified in terms of color rendering index. We saw that previously. So these quantities important while characterizing a white LED. And the highest luminous efficiency is obtained when these two lights, the short wavelength and long wavelength, the two monochromatic lights are complementary colors of each other. Okay, so if these two are complementary colors, then we obtain highest luminous efficiency. We have also defined luminous efficiency in previous lecture. The most commonly available white LEDs are the modified blue gallium indium nitride or gallium nitride coated with yellowish phosphor made of cerium doped yttrium aluminum garnet, which is expressed here, which is a powder suspended in the epoxy resin, which in the encapsulation we saw. Right, this is the encapsulation. So in that, what happens is that powder in this encapsulation, this powder is suspended, and this powder is made up of this material, which is nothing but the phosphor. Because as we saw that white LED is basically working on the principle of phosphorescence. And what is the driving source here? Driving source is this blue LED. Sorry. The driving source is the blue LED. Fine. So here the blue light, which is emitting the wavelength light with wavelength 450 to 470 nanometer from the LED chip, is converted by this phosphor to a broad spectrum, which is not, this is centered at around 580 nanometers. Okay, so what is happening is the phosphor, what is phosphorescence? You illuminate this phosphor material with a shorter wavelength, and it emits the light at longer wavelength. So what is happening here? This blue LED is emitting in this range 450 to 470, and the phosphor, after absorbing this energy, blue, the light emitted by blue LED, the phosphor absorbs and emits, that is re-emits the light, but at higher wavelength. What is the wavelength? 580. And now this 580 is nothing but the yellow color, and the blue color and yellow color are complementary colors of each other, and this combination of this blue and yellow basically produce the white light. Okay, basically produce the white light. Now then what happens is that these two colors, although they are going to provide the highest luminous efficiency because they are complementary of each other, but at the same time we are compromising on the CRI, because for obtaining good color rendering index, the spectrum should be as wide as possible, but here the spectrum is monochromatic because of the two colors. So in order to obtain the optimal results, that is the optimization of luminous efficiency, we want to obtain good enough luminous efficiency, at the same time good enough color rendering index. The tuning of phosphor concentration and thickness of encapsulant is done. These two parameters are varied to obtain good luminous efficiency, at the same time good CRI, because although we obtain highest luminous efficiency with combination of blue and yellow, it is going to result in low CRI. So you have to compromise in these two by optimizing these parameters. Okay, now I will close today's class and discuss the other topic in the next class. Thank you.